Thank you very much, Rodolphe, and thank you very much to all our speakers for a really interesting afternoon. So we now have 20 minutes of discussion time. So please do put any questions you have on the Zoom chat or in the Discord channel. One thing I'd like to start with is this role of communication and information, because I think in the variety of different topics we had, there were definitely a lot of mentions of sensing and communication through the environment, through active sensing, perhaps with Catherine's work, through passive interactions with Mike's work, and then with Amanda's kind of emergent information gain, and perhaps Josh also with these xenobots automatically, again, communicating through the environment. So I'm wondering your thoughts on, is there a hierarchy of communication with different, either with yourself, with the environment, with other other organisms that affects your level of intelligence or your capabilities, or what do you perceive to be the most important element of communication to create increasingly intelligent embodied systems? I don't know if anybody would like to start us off on that topic. Rodolphe, sorry.
I'll try to be short, but I think the most obvious one is the fact that if we want to go from conventional robotics to embodied intelligence, we need to make sensings and actuations much more multi-scale. And this is, I think, a grand challenge to see how we can sort of multiplex and communicate at very different scales, and how can we make those scales vary both spatially and temporally, very dynamically.
Catherine, I think that touches nicely on your list of requirements for sensing and starting to bring into those multi-dimensionality and multi-modality approaches.
Yeah, it definitely touches on many things I talked about. I was struck by Rodolphe's presentation, because I haven't thought that I'm doing neuromorphic sensing or computation, but many of the strategies that we've adapted towards are event-based, taking inspiration from neurophysiology, because we've just found it to be much more reliable than trying to respond to the steady state levels, which is what people have typically done with like a force sensor. Things drift, they're constantly changing, and the real world is so messy and ugly that we're really looking for patterns, which is basically like these thresholds, but probably doing it in a more clumsy way. I see Kirstin and Mike also nodding. Maybe they have something they want to mention.
It brings me great joy that you don't put additional constraints, because software sensors are already very hard to make.
Yes.
At least for me, like when I think of multi-robot systems, right? So I talk a lot about how they can communicate for the environment and really treat the environment as a database, like straight up a database. Like how often can you read and write from it? You know, how temporal is the information you put into it? But I think there's also something to be said for the fact that if robots can truly sense or even communicate, like right back to the environment, right, then robots can also start becoming more integrated in the ecosystem that they're deployed in, right? So, you know, agricultural robots could start actually, measuring signals from plants and, measuring signals for animals rather than trying to like abstract away from them. I think that's a really interesting sort of direction that some roboticists are moving towards, at least.
I think definitely accounting for the environment in our system, and that as a source of information and a two-way communication source is really fascinating. And Amanda, I think you're perhaps at the other end of the spectrum of kind of not focusing on the environment, but very much considering the communication between agents and how that emerges.
Correct. Well, right. So one way we view communication in within kind of our perspective of things is we're trying to solve problems which nominally can only be solved if you have global observability. Yet agents often only have partial observability. And so we try to train these communication policies so that the agents can share with each other the information that they believe is relevant, so that every single one of them can locally compose a view of the world that is sufficient to it to take near optimal actions. So it's using communications as a tool to reconstruct that global observation that they don't have at their disposition.
I think that's selectively finding the information you need for success as an individual in a population is that's interesting.
And the problem, the reason I hope this was somewhat clear through the talk, the reason we're doing this through data-driven methods is taking this apart through first principles approaches and understanding what exactly needs to be communicated at what point in time for many different applications is actually very difficult. And hence we're kind of throwing the kitchen sink at it by doing data-driven methods. But it has shown to be very powerful, and we're now kind of working at it from both sides. So trying to understand what exactly are the limits if we go from a first principles-based approach, and if we tackle it from a data-driven approach, can we actually backtrack it to understand what has been learned through the data-driven approach, and was it actually solvable in an easy way through a first principles-based approach?
Josh or Mike, I don't know if you have any thoughts on sensing and information communication.
Just to add on that, I think I was re-inspired this morning by seeing some of the state-of-the-art in soft robotics and collective robotics. And one trend I've noticed recently is robots are inheriting a richer and richer inner life. So Rodolphe mentioned hierarchical sensing. You know, if we talk about the environment for organisms, one of the most interesting and complex and challenging environments is within, not necessarily without. And you can view a lot of what's happened in, you know, large scale macro evolution is organisms exapting their adaptive processes to deal with what's happening within to what's happening without. If we look at, you know, traditional robotics, often robots, you know, don't have a very interesting inner life. There isn't a lot of interoceptive sensing, but I think we're starting to see more of that. And I think that's going to make things very interesting in terms of embodied intelligence, being able to grapple with, you know, things happening within and without simultaneously.
Yeah, I think the only thing I'll add on this sort of point of sensing here is that, you know, I think one of the things that has driven us traditionally to build robots the way that we have, with sort of rigid components and very well-defined defined joints, is exactly this question of sensing and modeling your state, right? It's when sensors are expensive, you want as few parts of your robot to move as possible. And there's also, you know, you can apply larger forces and achieve sort of very dynamic motions. But when we look to nature, there's this opportunity when you have the ability to have more sensors throughout your body to really do more interesting things and maybe solve different types of problems that our traditional designs have been able to solve. So I think these two things really do come hand in hand. And the work that we've done so far in sensing has also taken a sort of learning. We've realized at some point that you're not going to come up with some basic model for exactly the reason that everyone else is saying here. That's always going to work, and you really have to do some learning or other approaches to figure out how to deal with that sensing.
Yeah. Actually, that nicely leads on to coming on to the point I think Josh started us off with, of this idea of kind of conventional AI. What can it not do? The xenobots is a beautiful example of that. But we very clearly have advantages, and there are very clear contributions of conventional AI in addition to this maybe embodied intelligence. And should we try and bring these fields together? Should we develop them in isolation? Or how do we bring them together such that we perhaps don't lose the benefits of both? I wonder, Josh, if you have any thoughts.
I think, well, on the biology, you know, the biology side, obviously has a head start on us, a 3.5 billion year head start. Very adaptive, again, interoceptively and exteroceptively. It's surprising, actually, there are a lot of biological tissues and biological constructs that actually will work happily with, you know, non-biological constructs under certain conditions. I think at a surface level, it's often assumed that, you know, living and non-living components don't work well together. But I think we're learning that is not quite the case. And there's just so much, I think, that can be done at the intersection that will inform embodied intelligence.
Rodolphe, sorry, did you have anything to say? No, sorry.
Well, I guess my biased view is that AI is very digital and has drifted apart from animal intelligence further and further over the last 50 years because it has become more and more digital. And I think it's very striking in all the bioinspired examples that we have seen to see how much and I think that's a great challenge of embodied intelligence, is how to, you know, use the digital computation to at the same time make use of physical sensing, and how to combine the two. Yeah.
think interesting is we're so limited also by our limitations in sensing technologies, in our limitations of biology. It's really exciting the work you're doing, Josh, but we've got to push on both, I feel like, the fabrication and the development of new technologies to bring us up to a point where we can also exploit these kind of non-conventional techniques in addition to the more conventional approaches. Amanda, I wonder if you have any thoughts on, perhaps you work slightly more closely to the AI side, on how, from your perspective, we can bring in perhaps some of the physical embodiment approaches to what you're doing, or are there any limitations from a technological perspective that really prevent that kind of research?
That's a very open-ended question.
Yes,
not quite sure how to tackle that one. So are you thinking about how to optimize the morphologies of the robots so that the learning is more they are more amenable to learning processes?
Or is there a technology that limits you from the physical world from performing perhaps physical experiments that allow you to explore, for example, does the variation of the morphology or the environment affect what you're doing? Or is it really, I mean, there's a lot of already very exciting work to explore, but is there a sensing technology or a hardware technology that would really change the kind of work you can do?
Well, let me put it this way. I don't know if you're familiar with the sim to real problems. So often, so for all of you who've been involved with machine learning methods, they don't tend to be sample efficient in the sense that you have to collect millions of samples in order to get a policy that is able to do something relatively basic. So rule back of the envelope calculation for the formation control example I showed you, if we would have trained that system in the real world, we would have been training it for half a year nonstop. So obviously that's why we use simulation to train the policies. Now, coming to your question of physical embodiment, when we have these policies that are trained in simulation, we kind of cross our fingers, so did I, plop them onto the real robots, and expect the policies to do what they did in simulation. Now, the real world doesn't correspond to simulated world for many, many reasons. In the vision community, we know that they've been developing photorealistic simulators to reduce that gap. In robotics, it's much more complicated because there's not only the sensing, but there's the whole world around the robot. There's friction. In our case, we're really interested in the communication aspects, the delays, everything that happens in the real world that is really, really difficult to model in simulation. So to your question of real robot embodiment, the most common approach to reducing the sim to real gap is making simulators more realistic or working on the simulation side. Now, maybe if we could look at it from the other perspective, from the other side, and think about, okay, what is it that we can do in the real world or in the workspace that can make can reduce that gap that way around. But we have to be able to do it in a targeted way, because obviously we don't want our real world to look like simulation, but maybe there are some small things we can do in the real world that would reduce that gap the other way around. So there is an optimization we can do perhaps from that perspective as well.
Thank you very much. So I just wonder to finish, and also to touch on the discussion in the chat on that sensors are such a critical in technology, and it's preventing a lot of the work we want to do. If each of you could comment on, is there one technology or one research direction that you think would achieve a fundamental step change in embodied intelligence, to specifically to your work? Oh, Kirstin, what would be a fundamental game changer?
Can I pose a contrary view a little bit? This is a little dangerous. I don't want to go against Mike Tolley or from you, but I mean, I think like actually sensors have come a really, really long way in the last 10, 15 years, right? Like, I mean, I can now give my students a time of flight sensor for like $10, right? I get so much more information in my robots than I used to have for like no money at all. We can make our own soft pressure sensors and stuff. They're not super reliable, but we can make them. So sure, more information is always better, but I actually kind of feel like I'm not sure we're yet at a point where we fully exploit the amount of perception that we can get compared to the types of sensors that we could stick on a robot if we wanted to, right? I mean, we could always be greedy and add more sensors, but maybe we can be more clever about how we process it. I wonder if there's some work to be done to be catching up.
So from your perspective, what would you find is the biggest challenge that you have to overcome working kind of collective robotics?
So what we're really interested in, right, is the idea that if we're if we carefully couple the physics and the dynamics of all the robots, right, can we actually get away with having to sense the rest of the world and just rely on proprioception alone, because the robots are all affecting each other, and still extrapolate what's happening in the rest of the world? So, really sort of exploring what added benefits we get from having many simple robots work together, I think is part of the holy grail, at least of my narrow field.
Josh, sorry, you raised your hand.
I just wanted to call out, some of the non-intuitive twists that our respective fields are taking. If you go back to the cybernetics age, Gordon Pask did a lot of work on, designing materials that actually started to act as sensors. So, for those of us that are steeped in, traditional robotics, the assumption is you buy a sensor, you embed it into a machine, you cross your finger and you hope for the best. But as we start to push further and further into more and more interesting, complex, non-intuitive materials, we may be able to recapitulate what biology did, which is design, or evolve structures and behaviors that are able to capture a wider and wider range of phenomenon from the external world. And I think some of those sorts of things are on the horizon, and it's going to, I think, completely change the conversation around sensing, actuation, power, all of it. So I think a lot of what's happened in traditional robotics is not necessarily a good guidepost for what's coming.
Mike.
Yeah, just to add quickly on that, I think that was a good point, Kirstin. Sensing, the cost of sensing has definitely come down. I think one thing that's really exciting here and sort of relating to what Josh was saying was the opportunity for digital fabrication to build sensors within a body, throughout a body, as we build the system, right? And I think there's been some nice work from Disney research showing, looking at how you can have sensors all throughout a body and decide where the best place is based on actual simulation of the body. And this also relates back to some of Josh's nice work where you're sort of co-evolving the body and the brain, and I'm very excited about the opportunity of co-evolving sort of sensors that you can assume can be anywhere because you can, sort of print them or whatever it is.
Very nice. I think that's a very nice thought to wrap up with. Would any of the speakers like to make any other final comments about the discussion we've had? No? Perfect. Well, I think all that remains is to really thank you very much all for joining and your fantastic presentations. I think they've really contributed a lot to what we're doing and also the questions we want to answer. So thank you all once again. And we now have about a 13-minute break before we will dial back for the final plenary speaker of the day. So yes, thank you again to all the speakers, and we will see you in just over 10 minutes. Thank you.